better results than the bare receiver tube. And the powder coating, that is the chrome coating over the tube surface, performs better and absorbs better radiation. And the positioning of the tube on the focal line is very critical. And the slight deviation from the focal line will affect the performance drastically. And then the maintenance, especially like the coating and the vacuum that that is created between the absorber tube and the glass cover. So as I highlighted before, that the working fluids, it can be water, it can be nanofluid, and it can be other heat transfer fluids. And there are a number of heat transfer fluid, and it can be molten salts and the salts with nanofluid. So that depending upon the application, if our application is not very high temperature, then the water can serve as a working fluid. And if our temperature requirement is higher, then we need to take a working fluid that can boil, or that boils actually at a very high temperature. So that molten salts are the one example. And then the new category of the working fluids are like molten salts with with nanoparticles, or that we call the molten salts with nanofluid. So that basically enhance the properties of the molten salts as well. So the nanofluid are like again, like it has been shown in the literature that the nanofluid can perform better than the pure water in terms of the heat transfer capacity, heat carrying capacity. So the nanofluid, as we know them, that it is a mix of nanoparticles in the base fluid, and that makes it nanofluid. So the suspension of the nano-sized particles in the base fluid, and that we call the nanofluid, the nano-sized particles colloid not only enhances the stability of the suspension, but also enhances the contact surface area between the particle and the surrounding liquid. And that is basically the all purpose of using the nanofluid, so that you have a very high surface area, and that is equivalent to the number of nanoparticles and the surface area of each particle. And again, like there are different theories that how these nanoparticles enhances the heat transfer. So the one of the theory is that it basically increases the surface area, and another theory suggests that it has a Brownian motion, so that the synergetic effect basically gives you a very high mixing of the fluid, and that is at the micro level, and that enhances the heat transfer. So nanoparticles, the commonly used nanoparticles are within the 10 nanometer, and the lower diameter size nanoparticles have better surface area to volume ratio, and that is by the obvious reason, like smaller the particles and the better will be the surface area to volume ratio. And nanoparticles are better suited as heat transfer fluids compared to the normal fluid, like it can be any oil, it can be water and other. And this statement is true when we talk about only for the heat transfer carrying capacity. Of course, like with the application of the nanofluid, there are other disadvantages, especially the pressure drop and the pumping power requirement. And we know, like as you increase the mass fraction or the volume fraction of the nanoparticles in any nanofluid, then your pressure drop or the viscosity of the nanoparticle increases exponentially. So that basically limits the application of the nanofluids and the application of the concentration of the nanoparticles in the base fluid. So mostly, like when we see this exponential increase, so we limit our concentration around 3 to 4% for most of the applications. So apart from the advantages the nanofluid have, the disadvantages are also there, and that is basically the agglomeration and accumulation of the nanoparticles. So over the time, these nanoparticles in the flow settles down, and that basically creates a problem. And the second is the high pressure drop. So basically you need higher pumping power. So there is a trade-off that when you are using the nanofluid, then how much is the advantage that you are getting, and then how much you need to spend on it during the operation in terms of the pressure drop in terms of the pumping power, in terms of the electrical energy. So the most common fluid that we use uh, in solar collectors, like the oil, the ethylene glycol, water, synthetic oils, linseed oils, olive oil, and engine oil. So these are the mostly heat transfer fluid that we use for different applications. And as for the solar application, as of now, mostly we are using water and molten salt for power generation. So these are the different nanoparticles, and that can be used to form the nanofluids, and they have their own advantages and disadvantages, and the thermal properties are depending upon the kind of nanoparticles and the volume fraction that you are using. So here are these different locations where we have these solar power capacity installed, like the one is the Noor, and then this is the power capacity of 510 megawatt, and which is using the molten salt. And then the other one is Ivanpa Solar, which is we are using, which is producing 377 megawatt and using water, steam, so basically. And the other one is Solana, so which is producing 280 megawatt, and again it is using the molten salt. So as for the solar collector, that it is using parabolic collector, and this is using the power tower, basically the solar tower, central tower, and this is again using the parabolic. So the parabolic trough is still mostly used in solar power generation. So then we decided to do some experiments and basically prove the concept of a parabolic trough collector. So we decided to set up the experiment, and for the experimental purpose, we took the small geometry of parabolic, and here you can see like this is the parabolic trough collector, so which is of like 2-meter length, and then in the center of on the focus line we have this receiver tube, and then we have the circulation system, and then the instruments to measure the different quantities. So here is the geometric specification of this collector, like the focal length, the aperture width, the collector length, the rim angle, and aperture area. So these are the dimensions related to the solar collector. And then there are some standards that we need to follow when we do the experimental measurements. So the ASHRAE 9377 standards that we follow while doing the experiment and collecting the data. And some basic formulation that we use, like depending upon the solar intensity, and when you multiply it by the surface area, so you will be basically getting the energy that is falling on the trough. And then how much is your temperature rise from inlet to outlet, and then you multiplying by the capacity, and then you are getting the useful heat gain. So the thermal efficiency can be defined that what the useful heat you are getting, and then what is the heat falling on the trough. So here we have the two efficiencies, like the one is the thermal efficiency and the one is the optical efficiency. So optical efficiency is related to the transfer of radiation, that the radiation first coming on the trough, and then it is reflected to the receiver tube. So the amount of the radiation that is falling on the receiver tube, so that basically we consider as the Q absorber. So the Q absorb is basically higher than this, the Q useful. So here we define two efficiencies, one for the thermal purpose and one for the optical design purpose. The surface area of the receiver, which is related to the solar absorption and related to the convection losses to the environment. So these are the formulations that we use to understand that how and where are our losses during the experiment. So depending upon like whether you have a a steel tube only or whether you have a glass envelope over it. So when you have like just a stainless steel tube, then the stainless steel tube here have two losses basically. The one is the convection losses and another one is the radiation losses. So, so here, uh, so here we are having basically the convection losses and the radiation losses if we are using only the steel tube. And when we are using the glass cover, and glass cover, this space is evacuated, so we can minimize the convection losses here. So the only losses, only transfer is radiation from this surface to this surface, and from this surface onward, we have the radiation as well as the convection losses. So these things we need to understand when we are using the evacuated tube. So what we can minimize here is we can minimize the direct convection losses from the absorber surface. Of course, there are convection losses from this glass surface, but that convection losses from the glass surface are very less, and most of the time that can be minimized to basically to develop the reduced modeling. So the nanoparticles that we use for our experiment, it was aluminum oxide, and we mixed it with the water. So we obtained the 20% concentration of aluminum oxide particles in water, and then we diluted for our experiments as per our plant scheme. So when you make the nanofluid concentration, then we need to find out like what is the equivalent properties of the nanofluid. So we calculated densities. So these are all like standard expressions that is commonly available in the open literature to find out the properties of the nanofluid based on the properties of the components, like this is the density of the nanoparticle and this is density of the base fluid, and then depending upon the fraction of the nanoparticles we can use the formula to find out the density of the nanofluid. And similarly here for specific heat, viscosity and conductivity. So when we prepare our solution, so we prepare it for 0.1% concentration, 0.2, 0.3 and 0.4% concentration. And then we listed out like what are the equivalent properties when we have these concentrations, like when it is a pure water, so we use the water density is 1000, and then a specific heat, and then thermal, and this is thermal conductivity and viscosity. And when you are adding the nanoparticles, so we see like the viscosity is going up. However, the specific heat is going down, and the density is going up, of course, and then the conductivity is also going up. So these thermal properties, if we see like there is enhancement in thermal conductivity. So if there is a convective heat transfer, so that will be increased with this, and the specific heat uh, is slightly going down. So that means like your capacity of the fluid is going to be down a little bit. So when we did the experiment and then we observed like the solar radiation, and we started the experiment near about 11, and then we ended it about 2 p.m. and then we saw that this how the solar radiation is varying. So you can see the solar radiation variation here, and which is normal at any other place as well. And we know the different reasons like this as the sun comes uh, because of the environment, like if it is directly falling on the surface that where you are measuring, or it is falling through the angle. So here we see like there is a variation of the solar radiation, and then how we are basically getting the temperature rise. So the inlet temperature, how is it increasing? And then outlet temperature, how is it increasing? So here again that we see, so the once we did the experiment with the stainless steel tube, and then we did the experiment with the evacuated tube receiver, and then we observed this variation. So this variation is basically following the solar radiation. Like if the solar radiation is increasing, then the temperature is increasing. If the solar radiation is decreasing, then the temperature is decreasing. And that is with the obvious reason, because the fluid is absorbing more heat when the radiation is more. And however, this shift, uh, like the peak of the radiation and the peak of the fluid temperature, that might be slightly different, and due to the different reasons, like the one is the diffuse radiation, and and other is like the time lag uh, while you doing the experiment, then how your readings are actually reflecting the instantaneous heat flux. So when you have a solar tube and then you want to measure the temperature across the surface, so you see like here the solar radiation is falling on the trough and then it is reflecting. So it is basically reflecting only on this angle. So you will see like this is the portion where the temperature is higher, and then the upper portion the temperature is smaller. So this is again a challenge in the solar absorber tube design, that somehow you have to design a solar absorber tube in such a way that there should be the temperature uniformity. So as we see here that the temperature at this point is higher and the temperature at the upper portion is lower, and which is basically creating a thermal gradient in the metal, and that may produce thermal stresses, and that is basically deteriorating for the material point of view. So again, like there is a lot of research to how to minimize this, and that can be basically the many articles suggested like it can be minimized when you have a secondary reflector. So the radiation is basically coming on the trough and then it goes to the secondary reflector and then falling here. So basically you can distribute this reflected spectrum throughout the circumference of the receiver tube. And there are different other ways of to basically maximize this uniformity of the radiation. So, but now we are not going into that detail. So this is our variation, temperature variation on the circumference, and then along the tube we measure the temperature, and here we can see that along the tube surface the temperature is increasing, and with the obvious reason like the fluid is flowing in this direction, so the temperature is increasing along the flow direction. So when we compare the performance of the two receiver tubes, that this is stainless steel bare receiver tube and this is with evacuated cover, so we saw that the evacuated tube basically can generate more temperature rise than the bare stainless steel tube by a few degrees. Like here we can see like almost 1 degree, but the difference is not very high. And the reason is like because this is just an experimental setup. The length of the tube is only 2 meters. So the effect of this steel tube and the evacuated tube may be different, and that again need to be experimented when you have a very large tube for power application. So when we see like as you're increasing the flow rate, so the temperature rise is decreasing with the obvious reason, because the solar radiation which is falling is almost same, which is changing slightly, but which is almost same, because the experiment was performed when the sun is the solar radiation is toward the higher side from like 11 a.m. to 2 p.m. So when you're increasing the flow rate, and then the temperature rise is of course drop. So this is again a critical factor, like how much flow rate you're basically you should be, so that you can get the desired temperature for your application, whether it is a desalination or whether it is some other industrial application. What is the effect of the flow rate on the thermal efficiency? So that is interesting here. Like, although as we saw in previous graph, like here, that when you're increasing the flow rate, your temperature rise is decreasing. However, if we see the thermal efficiency, and this is increasing with the flow rate, because this is related with the losses. So if the tube surface temperature is less, then you are basically having less losses to the environment, because the ambient temperature, let's assume that this is going to be some temperature which is lower than the surface temperature. So higher the difference, then higher will be the losses, whether it is convection losses or radiation losses. So that's the reason that we are getting here higher efficiency when we applying the higher flow rate. But of course that the higher flow rate is not always uh, desirable, because ultimate objective here is to basically get the higher temperature rise of the fluid, so that can be used for uh, some applications. So, and this is the useful heat gain. So again, like the heat gain will be increased as the losses are going down. When we increase the flow rate, the temperature of the surface temperature of the tube is going down. So the useful heat is also increasing here. So we did the experiment with the this alumina nanofluid, and we did for the stainless steel tube, and we did for evacuated tube, and then we saw like these trends that as we are increasing the nanofluid fraction, and the temperature rise of the working fluid is increasing, and at some point it is increasing significantly, like it's increasing by almost 2 degrees Celsius. And remember that this is just for a small length, just 2-meter length of the tube. So like for industrial application, when you have a tube length of like 50 or 100 meter, then the temperature rise will be significantly, the temperature difference will be significant. So we did the experiment for the steel tube, and then we did the experiment for evacuated tube, and observe the difference here. So the trend remains the same. However, the degree of temperature rise is high in case of evacuated tube, but the trends are same. So so degree of rise, like as you can see here, that it is reaching, it is going to be like the difference from almost like 6.5 to 10. So this rise is more in case of evacuated tube, but the trends are same, that with the increase of the flow rate, the temperature rise is going down. And then we observe the trends for the thermal efficiency. Like here we are increasing the flow rate, and here we're measuring the thermal efficiency. So as we see here, like there is a sharp increase, and then from this point, the rate of increase is less. So as we can see, like here in this portion, when you're increasing the flow rate, your temperature rise is dropping sharply. So that basically reducing the losses sharply. But here the temperature rise is not dropping to that rate, and then here we are getting the efficiency rise, but with a small rate. And almost similar trends we can see for the evacuated tube. So basically, if you look at the trends are same. The only difference is in the degree and the magnitude of the quantities. So here we can conclude the results from this experiment, that if we are increasing the flow rate, the temperature rise that we are collecting in the fluid will go down. So you have to adjust the flow rate depending upon your application. And the nanofluid can give you enhanced performance, and can basically increase the heat collection. The thermal efficiency is higher. And but of course, like there are some drawbacks that is still we need to explore, and still I need to do more experiment, that how much is basically the loss in the pressurize, in terms of pressurize, in terms of the pumping power. So that can be still need to be assessed, and then we have to do some exergy analysis, like what are the benefits that we are going to have when we are using the nanofluid. On the one hand, that we are getting the higher heat collection, but on the other hand, that we are putting more input power. So how much is basically gain, and in terms of the economic analysis and in terms of the exergy analysis. So here is basically the end of this experimental setup, and then I have a second part of it. So I don't know, like if anybody has question in this part, then probably we can do, or we can do the question and answers at the end of both the sets. Yeah, the moderator can suggest, like, shall I continue with it?
Okay, continue, Afzal.
You may continue for 5-7 minutes, 10 minutes, and then we will have some discussion.
Okay, good. Thank you.
We can take session up to 4.
Okay. So next in the series was like the experiments for the photovoltaic thermal. So what is photovoltaic thermal? So we all know, like the photovoltaic, that is the PV panel. The PV panel is a simple a silicon panel, and that basically connects the silicon cells in series and parallel to give the required current and voltage, as you can see here. Right. So the PVT panel is a panel like that have a electricity generation as well as the solar collection in the same setup. So here you can see, like this is the details parts for the PVT panel, and like I took just for any standard one, like at the top you have like a tempered glass, and then after that you have encapsulating film, and then you have a solar cell, and then again you have the encapsulating film, and then below that you have a basically absorber sheet, and then you have a insulation. So as you can see here, like here we have a PV panel. So the PV panel is basically getting the solar radiation, and the silicon, it is falling on the silicon, and silicon through the conduction, it is transferring the heat to the sheet at the back, and from the back it is going into the absorber plate, and this is my absorber plate for the thermal purpose. So this is the thermal part, and this is the electrical part. As you can see in more details here, like here this is the glass, and then we have encapsulating film, and then we have this PV cells, and then again encapsulating film, and then here we have these copper pipes attached with this this plate. So that can be used as a thermal collector. So the fluid is flowing in these pipes and collecting the heat, and at the back uh, we have like it can be any wooden cover or any metallic cover with insulation. So there is insulation also there. So this was the conventional design, and since like I was working on the micro channels and mini channels, and then I decided like uh, if we apply the micro channel and mini channel concept here, would it be more advantageous or not? So if you remember from Dr. Om Prakash's lecture day before yesterday, that he basically emphasized that all electronics they need to be kept at a certain limiting temperature, as well as they need to be kept at a certain temperature gradient. For example, like uh, the temperature should also be limited, as well as the gradient, like along the electronic circuitry, the temperature should not be changing too much. So the temperature gradient and the temperature, these are the two factors that basically affect the life of the electronics, and be it a like a electronic chip that we have in our computers and mobiles and so on, or be it a PV cells. So the concept is same, that what we need to do, we need to basically minimize the temperature, and we need to basically enhance the temperature uniformity along the surface of the PV panel. So what Dr. Prakash presented, that the main focus was basically uh, uh, on the to maintain the temperature uniformity uh, for the PV cells. Of course, there were other things in his talk that was very wonderful. But as for the PV cells point of view, the target was basically to keep the temperature same. So here in this case, my target was that how to collect that solar uh, energy that is basically not absorbed by the PV cells. So what we did, like, this is our PV cell, which is taking the solar radiation here. And then below that, we designed here the micro and mini channels, and due to some like fabrication constraints, we could not go to the micro channels. So what we did is basically the mini channels. So we designed here the mini channels in a metallic plate, and then we are then these channels are basically carrying the fluid, and that fluid basically taking away the heat that is basically transpiring from this solar panel to this absorber plate. And then at the back we have insulation, and then we have like a casing for the entire module. So this is our plate design, and this is the cover of the plate. And as you can see here, like the dimensions of this panel. So this plate design is almost, the size of the plate is basically same as the size of the panel, because this plate is going to be put on the back of the panel to collect the solar radiation that basically not absorbed by the PV cell, because the PV cell is only absorbing a certain spectrum of the light, and the infrared is basically just passed in the form of heat through the PV cells. So here is some fabrication details, like we have this PV panel, and then at the back of the PV panel we put this absorber plate module. So absorber plate module is basically the plate with grooved channels, and there is a cover plate, and then there is inlet. There are manifold for the inlet and outlet of the fluid. And then we put the insulation over that, and then we put the wooden cover over that, and then connected the inlet and outlet uh, pipes to basically circulate the fluid inside the channels. And for the measurement purpose, we put certain thermocouples at different places, and the pressure sensors, and the voltmeter and temperature measurement, flow rate measurements, all the things. And of course, there is a flux measurement also. So this is our experimental schematic. And then we see like how the performance is in terms of the efficiencies, in terms of the temperature rise, in terms of the solar collection. So here we see like as for the electrical power generation of the PV cell, the power generation remains almost same, and the efficiency. So here, if we compare the power generation from like 8 a.m. to 4 p.m., so it is almost same, like if you see like starting from near about 60 watt, it is slightly increased, and then it is falling to 20 watts. So here again, like it is slightly increased. So there is a slight for the reason, as we know, like uh, the the characteristic behavior of the PV cell is like that it is more efficient at the lower temperature, and as the temperature is increasing, the efficiency is also going down, as well as it affects the life of the PV cell. So, but as for the effect doesn't seem very significant. It's a just slight effect on the PV power generation. But when we go for the efficiency, then efficiency again, that it doesn't show a very high difference in the efficiency. And the reason is that because these PV modules are uh, is not very dense PV modules, so it's low power PV modules. So that is basically not very highly integrated. circuits that can generate a very high temperature inside. So the power generation and the efficiency of the electrical modules remains almost same. Of course, there is a slight improvement in the power and efficiency in case of PVT. In case of when we are applying the thermal absorber at the back of the PVT. So the first case, as you see, this is like this is just the PV panel, and the second case, what you are seeing here is the PV panel with the back absorber plate, and what we are calling it basically the PVT panel, and this is simply we are calling it PV panel. So like here, if there is no this back absorber, then we are calling it just a PV panel, and when we have this solar absorber at the back, then it becomes a PVT panel. When we check the surface temperature of this PV panel, when we have only PV, so here we see like when we did the experiment with the PV, and there was the temperature rise up to like 53 degrees Celsius here, and then 34 degrees Celsius, and so on. And when we apply the absorber plate at the back, the maximum temperature rise was like near about 35 degrees Celsius. So at the center, it is 35. So it significantly reduced the temperature. So the surface temperature, if we see that when we are having only the PV pen and we have the PVT panel, so you can see that there is a significant surface temperature difference. So which is almost, which is basically slightly more than the 10 degree Celsius. So, and there is another thing, like when you are using the PVT, you are basically circulating the fluid in the many channels. So there is a significant pressure drop because of the nature of the channels, because the channels are very small and there are a number of channels. So the pressure drop is also high in these channels. So as you can see here, like the length of the channels is not too much. It is just like 1.6 meter, but the pressure drop is significantly high when we are using the mini channels here. As for the thermal power generation and the thermal efficiency, so the thermal power generated in terms of the water heating that is flowing in the panels, and the thermal efficiency, we measure that what is the solar radiation falling on the panel, and then how much is the energy collection by the fluid. So we apply those formulation, and then we found that the thermal efficiency comes out to be like the peak efficiency, as you can see. So this is our outlier, so we can ignore this, but these are mostly showing the general trend. So the peak efficiency that can be obtained like slightly less than 80, so mostly between the 60 and 80%. So of course, this is like a case of a flat plate collector. So here with this much efficiency, and then we can collect this much power. But of course, like we cannot have a very high temperature rise in this case because it's a flat plate collector, and the length of the panel is equal to the length of the PV available in the market, which is mostly in the size of like from 1 to 2 meter. So sometimes it is 1.6 meter, and there are several sizes, but mostly they are lying in this range. So here is the end of my talk. So what we can conclude from this, the second set of experiment is that the efficiency and the power generation doesn't affect much, but of course, when we apply the solar absorber plate at the back of the PV panel, we can collect a good amount of heat with good efficiency. That is about 60 to 80%, and with the temperature rise of about I thought I think the temperature rise is not here. So yeah, this is one. So thank you very much once again for giving me a chance to show my research here. And if you have any question, any clarification, so now I think the ball is in your court now. Thank you very much.
Afzal, for a nice presentation. So anyone from the audience, if want to ask any question, so please you can ask.
Yes, sir. I want to know that, sir. In a parabolic trap collector, you have shown optical efficiency formula, that is QA by QI. Then, sir, how I calculate the QA?
Here we use this QA. The QA is basically these are the terms that we need to know when we want to calculate the QA, like the reflectivity and the reflectivity of the reflecting mirror, and the absorptivity of the receiver tube, and the angle factor. So these things in my experiments, I have not measured it. So I took this formula as to understand that how the optical losses are basically behaving. But when you want to measure it, then we need to basically measure these quantities.
Okay, sir. Okay, sir. Thank you.
Welcome.
Sir, uh, I want to ask about the economics of this solar panels. You compared the PV panel and the PVT panel, sir. So
Yes.
cost-wise, how much is the difference or the increase in cost? There will be certainly an increase in the cost with using this PVT panel. So how
Yes,
much?
like as I said, like these experiments are still in the preliminary stage, and we have not carried out actually the economic analysis and the trade-off analysis. As I said, like during my presentation, also like we need to explore this, that how much is the advantage we are getting on our spend on the absorber plate, and on the fluid that we are circulating. But anyway, for any collector, we need to circulate the fluid. For any collector, we need to have an absorber plate. So we are having the absorber plate at the back of this solar back of the PV panel. The advantage is that, like at the same time, we are getting the electricity, and we can have the solar collection in the form of heat as well. So this is the advantage of the PVT. But as for the economic analysis, that needs to be carried out.
Yeah, sir. Yeah, I fully agree with this thing. And one more thing, efficiency will also increase by using this temperature uh,
Yes. Yeah,
to be.
this is basically with the characteristic nature of this any electronics. Like when you see like the electronics which is made of like PN junctions, and which is like there are some already available in the open literature. There are some characteristic graphs which I have not included in this presentation, which shows like that how this PV panel or PV cell efficiency changes with temperature. And there are studies also, like when these PV cells working under higher temperature and working under lower temperature, and then how their life prolongs. And so basically the durability is also affect. So there are two factors. One is the temperature that affects the life and durability, and the other is basically the gradient that is developed on the surface of the PV. So these two affects the life and durability of the PV, as well as these affects the efficiency of the PV. So the objective is from those studies, what we can get is that we need to minimize the temperature of the PV, as well as we need to minimize the temperature gradient that is developed on the surface of the PV. So the objective is to keep. So what we are using the PVT, so we are using the absorber plate at the back of it, so that basically serve for us dual purpose. Like the one purpose is that we are minimizing the temperature of the PV, so that basically increase the life of the PV, as well as we are getting the solar collection.
Yes, yes. That will give you the double benefit, sir.
Yeah.
And
Okay,
sir, I wanted to know one more thing. If you have that experience in that field, because you are in Muscat, I understand that is along the seashore in
Yes,
Oman. So
yes,
that may
yes.
be interesting if you can share anything in the field of this solar thermal, meaning desalination. I am very much interested because we face acute shortage of safe drinking water. So using this technology, desalination plants may be installed there. If you have some experience.
I do not have some experience on this, but I have like some information that the solar thermal desalination is basically we have not started here on commercial scale. It is still in the experimental stage, and most of the desalination plants that we have here is basically run by the fossil fuels, and uh, and yeah, but it is in the experimental stage, and maybe there are other researchers who are doing research on the desalination size, and they are basically looking at the feasibility of this lab scale plant using the solar energy. Some of my colleagues are doing on this.
Using this solar thermal technologies.
Yes, solar energy for desalination.
Otherwise, using fossil fuels to desalinate the water, so that will be not much wise. Uh, Actually, renewable energy using desalination will be better, I think.
Yeah, I mean, using renewable energy is better when you are like in any of the field, like whether you are doing air conditioning, whether you are doing your transportation. But it depends upon like what you have at your hand and what you can afford. So, as a Middle East country, what we have in our hand is fossil fuels. We can spend on that. We do not have that ready technology that the solar energy can be applied for desalination on a mass scale, on a commercial scale.
Yeah, sir. Thank you.
Welcome.
Thank you, Anand. Anyone else? Yes, please. You can say about the lecture, or you can, if you have questions that you can ask. Das sir, are you here? Yes, madam.
My question to Dr. Afzal sir, you have really presented a very basic things which are, I mean, to us, for, I mean, we are not in the solar, this thing, we are in the waste to energy, but it is a very knowledgeable presentation, sir. One thing which I would like to
Thank you
know,
very much.
the ambient temperature over there in average is around 50 to 52,
And,
the
no, average temperature.
peak temperature, yeah.
Yeah. Okay.
How do you maintain that? How do you make the maintenance because of the seashore as well as for I mean, the wind and all that from the seashore? I mean, with that dust and all that which is coming on that one screen.
Yeah, we we do not have a very big installation for these purpose. And recently, in the last 10 years, we developed these kind of installations like PV field and the solar parabolic trough field. We recently developed it. And as of now, we are using very conventional technology to clean it up in terms of the dust and in terms of the moisture as well. And but you are right, there are other mechanism to deal with it, especially the PV panel can be cleaned with the robotic arms, and the solar trough can be protected in different ways, like either you keep the tube within the parabolic curvature and then cover it with the any transparent sheet, and then the transparent sheet like can be cleaned with the robotic arm. Like what I mean to say, if you have a parabolic trough like this, and then if you're putting the collection tube here and then you cover it with this, then this transparent sheet can be cleaned with the robotic arm. So this is how we can do the maintenance. But as of now, of course, because in Oman we install these facilities, especially this solar field which is using the parabolic trough. So this is imported technology, and then we do not have that kind of a we call it like this is not this kind of a parabolic trough. We have a conventional parabolic trough and we clean it using the conventional methods. I hope I answered your question.
Yes, sir. Yes, sir. Thank you. Thank you.
Okay, welcome.